Hey everybody, it's Ripley back again. We're going to talk today about indefinite integrals and what's called the net change theorem, but this isn't going to take very long. It's pretty straightforward. However, it's got some kind of far-reaching ramifications that we want to make sure that we discuss. Let's talk about an indefinite integral. So a definite integral is the integral from a to b of f of x dx, and this is equal to the excuse me, I just had a snack bar and I just choked on it. This equals the antiderivative of f evaluated from a to b, which is capital F of b minus capital F of a, or the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. This is FTC2. This is the fundamental theorem of calculus 2. Now, what happens if I have what's called an indefinite integral? All right. So, for example, the antiderivative of sine. Well, think about this. What is the function whose derivative is sine? Well, we know the derivative of cosine is negative sine, so I could just simply say negative cosine of x. But there's a problem. While this is an antiderivative of sine of x, if you recall from antiderivatives before we got into the idea of integrals, what I need to add is a c. Because if this c were 17, then the derivative of this would be sine x. If this c were 193 pi, then the derivative of this would be sine of x. So what I generate here is a family of functions whose derivative is sine of x. Okay? Remember, you can always check to see if your antiderivatives are correct or incorrect simply by taking the derivative, and you got to get back to the integrand. Okay? All right. Typically, a textbook is going to have some sort of table of integrals, or you can just look on the internet. This is the table of integrals that I brought up, so it seems to have everything that we need, right? The derivative of x is 1, which implies the antiderivative of 1 dx is x plus c. So on the left is, this is kind of cool because we've got the derivatives that you should know, right? These are basically what I refer to as flashcard derivatives. And on the right, we have all of their antiderivatives. And you can see the relationship between the two of them. All right? The thing I like about this table, which some tables, especially the ones on the internet, don't have, is they don't always put C on there. All right? All right, right on. So, look at this. We've got the antiderivative of x at the end. We've got the antiderivative of 1 over x, which is natural log of absolute x, cos, sine, et cetera, et cetera, et cetera. We got the whole thing. All right. I would make, well, you don't even have to make flashcards. What you might want to do is simply use your derivative functions, go to the other side, and remember, in other words, if you look, these equal signs end up being the integrands over here. So we just throw those in an integral sign, and then we've got, we know what the antiderivative is. Okay? All right, that's pretty easy. Now let's really quickly, really briefly, I know you guys probably don't want to spend too much time on this. Let's talk about the net change theorem. So this is the net change theorem, and it's a super straightforward theorem. You've probably already figured it out, but let me give you an idea really quickly. What happens if I take the antiderivative of v of t dt? Well, I know that this is from a to b. I know what this gives me is x of t made of b, which is x evaluated at b minus x evaluated at a, right? But what does this represent? This is the net change in distance. And we can build it using geometry. I can show you why. Look, if I know that v of t has meters per second, right? And this is going to be t, and this is going to be in seconds. Well, remember, all of this madness, this is v of t, right here, all the madness that we call, let's let this be a, and let's let this be b. All of the madness that we call integrals was built on rectangles. Let's change my colors. All right, here we go. Right here. So let's take that rectangle. The area of that rectangle we know is, if we just look at it through dimensional analysis, I'm not even going to use delta t or any of that stuff. I know that the area is going to have units meters per second times seconds wide. So it's meters per second high to get me up to v of t, and it's t, what did I do there? Times time in seconds. Cancel, cancel, and I get meters. Now we got to be careful because we got this negative. That's why it's net change, not chance, net change in distance, right? It would be you know, if I started at some value and I moved left and right, if I took the integral from a to b, that would tell me how far I ended up with respect to where I started. Let me show you. So if I don't even need that vertical line, whoa, throwing the pen around, what's going on here? Let's say that I had a particle and I knew its velocity and it started, I don't know what's going on there. It started at A and it went right, and then it went left, and then went right again, right? And then this would be at time. This is t equals a, and this is t equals b. I know that x of b minus x of a would be this distance right here. This is the net change. Now, if I wanted total distance, you guys remember this from, wow, for some reason I can't write change today. If we wanted the total distance traveled, then we would have to figure out when it stopped, take the net change from there to there, and then the net change from there to there, and then the net change from there to there. So this is net change. All right. Another example is, think about it this way. If I had a function that represented the flow of water in a river, right? And that's typically represented by, let's see, this is going to be dv over dt, and this is usually CFS, or cubic feet per second. And then over here would be seconds, so t equals seconds, right? And this is from A to B. Again, if I take the integral of dv over dt from A to B, right? So these guys go away, I get dv. So this would be v of b minus v of a. And what if I look at the units again? Let's change colors one more time. If I look at the units, I draw myself a little slice of action right here. That's what I'm going to refer to it down the road, by the way. I know that this is cubic feet per second times t seconds. Go by, and I get total volume, right? So this would be the net change in volume from A to B. And what does that really represent? It would represent the total volume of water that passed through whatever station you're using to monitor flow. Now, there's the net change theorem. The net change theorem is really very straightforward. It simply says the integral from A to B of f prime of x, capital F prime of x dx is equal to capital F of B minus capital F of A. All right, and this is the net change of, the net change of the quantity that you're talking about. Okay. All right. Now I use capitals in this case because it gets us. This is kind of a weird notation. This is worth talking about. Remember, the fundamental theorem of calculus 2 over here gives us these capital F of B's and F of A's because it wants us to make sure that we know that we're using antiderivatives. And if we wanted to, we could write this as little f of x. But in this case, they want us to make sure that we're understanding that we've got a rate of change. This f is not just some function, 2x plus 3. It is a rate of change of something. So if I'm taking the integral of, I don't know, the rate of change, if I go rate of change of carbon ions or molecules in solution, right? So this is per minute, right? I don't know, I'm titrating and I'm trying to figure out the rate of change of carbon, right? From A to B, and then these guys would cancel, right? And I would end up with capital C of B over C of A. And this would tell me the total amount of carbon atoms that I lost or that I gained over a time period from A to B. Okay, dimensional analysis is definitely your friend. If you can use dimensional analysis, like if this were carbon molecule or moles of carbon, let's say carbon per minute, and then I know that it's times minutes because that's the dimensions of the rectangles that we're using. These cancel and I get total carbon. But being able to understand that that's net change in carbon, which is kind of counterintuitive, but we're taking the integral of the rate of change of carbon. So we're basically taking the integral of the derivative, which is of carbon, which just gets us back to carbon. All right, like I said, super straightforward, not very difficult. This is a really easy section because you've already taken general antiderivatives in the past, and then with fundamental theorem of calculus, we linked the whole thing together, and life got good again. Okay, cool. Have a great day. Thanks for your time and attention. I'll see you in the next section.